let's talk about the identity and another operator which I'm going to introduce called the projection operator. Okay, the identity operator we've already seen in previous lectures, but I can write it out now a little more explicitly, and that is if we think of our 3x3 matrix case, then the identity I could write out as 1, 0, 0, 0, 1, 0, 0, 0, 1, like this. So this is just a 3x3 identity. I could do a 2x2 identity, or a 4x4, or a 10x10 matrix of, but I'm writing this out as its matrix elements. So the matrix elements for the identity operator have the diagonal have all ones, and all the off diagonal elements are 0. So if you think about it, if I apply the identity to some vector v, where now this is 1, 0, 0, 0, 1, 0, 0, 0, 1, and my vector is, I don't know, let's say x, y, and z. Then when I multiply row times column, I get back 1 times x is x, and then the 0 times y and z gives me zeros. In the next second row, the only one that survives is y, and the third row, the only thing that survives is z. So you can kind of see that the identity operator written as a matrix element is just ones along the diagonal and zeros along the off diagonal elements. If I want to write this in Bra-Ket notation, the matrix elements of the identity operator is now just the identity operator operating on some basis states j, which again returns just j. So we get I projected onto j, and we said that the inner product of this basis states of I and j gives me the Kronecker delta. And if you remember, the Kronecker delta is 1 if I is equal to j. That gives us the diagonal elements of the matrix, and it's 0 when I is not equal to j. So that gives us the off diagonal elements of zeros. Okay. So now let's take a look at the projection operator. Okay, so this projection operator now is, let me take my vector v, and I now want to take the sum of this, where I've now written the coefficients. I usually write the coefficients v sub I as the projection of I on the vector v. Okay, now if I rearrange this a little bit, so if I group together the sum with this basis I, the ket I, and the bra I, like so, then basically what that looks like is the identity operator. So I now have another definition for the identity operator in terms of basis vectors, where it's the sum of the ket I and the bra I. So now this is my another way of writing the identity operator. Okay. Now if I think about it, what I have up here, when I took the ket of the basis vector I and the bra of the basis vector I and multiplied it, or took the product with the vector v, what I'm doing is I'm projecting out the amount of v that's in the I direction, and then multiplying it times the basis vector for I. So I'm projecting out that amount of v on I. So therefore, I can write a projection operator P sub I as this combination of ket and bra basis vectors right here. So this is the projection operator right here. So now I can write the identity operator I as the sum of all projection operators P. So if I consider the projection operator I operating on a vector V, then what I get is that projection of V onto the basis I. So it's that coefficient VI, which we've used many times before, multiplied by my basis. So I'm projecting out the amount of V onto the basis I. I could also use the projection operator on the bra. Whoops. On a bra vector V, not I. Okay. So when I'm doing that, I'm writing down the projection operator as usual, but now I'm taking the inner product in the opposite direction. So I get the complex conjugate of the coefficient VI times the bra of the basis vector I, written in the usual way, like that. Okay. So the last thing I want to do now is consider the product of two projection operators. So let's say I have two projection operators, PI and PJ. So I'm going to operate with a basis J, project it onto the basis J, and then operate the result of that and get the projection onto the basis I. So I'd write that as the projection operator in the I direction and the projection operator in the J direction, like so. Well, now what I have is an inner product of I and J. And if you remember, that inner product of the two bases vectors I and J is the Kronecker delta function. Like so. So in the end, that Kronecker delta is just a number, so I can take it out front, and I'm left with now the ket in the I basis and the bra in the J basis. And so if I now operate on this on a vector, I operate this product on a vector V, I would get V like so. I would end up with IJ and the basis I times the coefficient of V sub J, but because I have the Kronecker delta, I now can swap that index and call J I, because the Kronecker delta is only going to be 1 when I is equal to J. And I get V sub I, like so. Okay. So this projection operator is just a compact way of saying I want to take the amount of a vector V and look at its projection onto a basis of, say, I or J. Okay. So in the end, what I have is this product of projection operator J and projection operator I together, in the end gives me a Kronecker delta of I and J times the projection operator in the J direction. So we'll come back to this in future lectures, where we basically take the projection operator and project V, the vector V, onto the J direction, and then project that onto another direction, say I.